In the diagram, the shaded triangle is a close approximation to the area swept out in a time dt by the line connecting the Sun to the planet. The area of the triangle, dA, is equal to half base times height, so in other words, r d theta is the base length times r the height. So that is just equal to a half r squared d theta. The rate at which the area is swept out, therefore, is given by dA by dt equal to a half r squared d theta by dt, and we'll call that equation 1. If v is the velocity vector of the planet at the point P, then the component of v perpendicular to the radial line is v sine phi, as shown on the diagram now. The displacement in the direction of v perpendicular during the time dt is r d theta, as shown on the diagram. So v perpendicular is just equal to r d theta by dt. So therefore we can write that r d theta by dt is equal to v sine phi. We can now substitute this into equation 1, and we get that the rate of change of the area swept out, dA by dt, is equal to a half rv sine phi. But rv sine phi is just the magnitude of the cross product of the vector r, the position vector, with the velocity vector v. Now you know that the angular momentum of the planet with respect to the Sun is given by the usual equation. L is equal to the vector product between r, the position vector, and the momentum, which is m times the velocity vector. M here is the mass of the planet. So therefore we can write that the rate of change of the area swept out, dA by dt, is just equal to 1 over twice the mass of the planet times the magnitude of the vector product r cross mv. So that is equal to the magnitude of the angular momentum divided by twice the mass of the planet. For the rate of area swept out to be a constant, in other words for dA by dt to be a constant, the angular momentum L must be a constant. The angular momentum L will indeed be constant because we know that dL by dt is equal to the torque, which is equal to the cross product of the position vector times the applied force. Now the only force acting on the planet is the gravitational force, and this is acting along the same line as the vector r. So since these two vectors are parallel, so to speak, their cross product is 0. Therefore dL by dt is equal to 0, and therefore the angular momentum is constant, and so dA by dt is constant, thus proving Kepler's second law.